Now that we've had a chance to look at velocity, both instantaneous and average, and since we've had a chance to take a look at what velocity versus time looks like on a graphical analysis, we're going to be looking at acceleration and deceleration, uniform motion and uniform accelerated motion. This lecture video is going to cover sections 2.4 and 2.5 from your textbook, as well as examples 2.3, 2.4, and 2.5. I want to make a special note that examples 2.6 through 2.9, which are also part of 2.5, are going to be covered in kinematics and problem solving, which will be a lecture later this week. So that means that we're not going to make it entirely through 2.5, only introduce the concept of when you would use two different types of problem solving. So when you hear the term acceleration, it's really just an explanation of when your velocity is changing. So acceleration is changing velocity. Most of the time in our everyday lives, we use the term accelerating to mean speeding up, and we use alternative language to talk about slowing down. But in physics language, acceleration is any kind of change in velocity. So if your velocity is changing, you are accelerating. If his velocity is changing, he is accelerating. One example of this, a popular example, would be a car that is able to accelerate from 0 kilometers per hour to 96 kilometers per hour. In our English system, that would be 0 to 60 miles an hour. That should sound somewhat familiar because just about any car commercial that you've ever listened to talks about a car's ability to accelerate from 0 to 60 in some amount of time. Because these are velocities, and because the velocity has changed from a car at rest to a car that is not at rest, this car can accelerate. So that means that acceleration really is just able to tell you how rapidly velocity is changing. So let's consider this situation right here. Our car that can change from 0 to 60 miles an hour, it's telling us that the velocity is changing. So that would be v2 minus v1. Alright, so that would be 96 kilometers per hour minus 0 kilometers per hour. That would be the change in velocity, but we want to know how rapidly the velocity is changing. So let's take an example where our car is making that change in a total of 6 seconds. That's a popular time for a car to be making that change in 6 seconds. So that means that the car is making this change from 0 kilometers an hour to 96 kilometers per hour in 6 seconds. So that means that every second that car is changing from 96 kilometers per hour divided by 6 seconds, that would be 16 kilometers per hour every second. That's the change that the car is able to do in that situation, and that would be acceleration. How fast is the velocity changing? Well, it's changing 16 kilometers per hour every single second. Alright, so what we're reporting here is average acceleration. Average acceleration is just the change in velocity divided by the elapsed time, and that should have been intuitive for you up here when we talk about how rapidly the velocity is changing. Well, we have to figure out the change in velocity and how much time it took for that change to occur. So we can look at average acceleration. We're going to follow the same nomenclature that we did for average velocity. We're going to use A for acceleration just like we used V for velocity, and we're going to use the bar to show that it's the average that we're calculating. So our equation for average acceleration then is going to be v2 minus v1 over t2 minus t1, or the change in velocity divided by the change in time, and that's going to be our equation for average acceleration. Just like velocity, we're dealing with a vector quantity, which means that acceleration happens in a direction. Right? If you're moving in the positive direction and you accelerate in the positive direction, right? If your velocity is in that direction and your acceleration is in that direction, then we would say that you have yourself a positive acceleration. Right? If you're moving in that direction and your acceleration is in that direction, right, then we would say that you had a negative acceleration. Right, so your acceleration is either positive or negative. That positive and negative value, it's very important for you to know, just tells you what direction your acceleration is happening in. And we only need the positive and the negative because we only are dealing with one dimension. So that means it's either positive on the axis or negative on the axis. All right, so just like velocity, I'm not going to go into a terrible amount of detail about this, but just like velocity, there's average acceleration and instantaneous acceleration. And instantaneous acceleration is just analogous to velocity. It's taking the consideration of what that changes over a very short period of time. So that would be just that moment, as that moment approaches a time change of 0. So instantaneous acceleration can be different from average acceleration, just like instantaneous velocity can be different than average velocity. And just a quick important thing to make a note of. So let's take a look at an example. We're going to take a look at example 2-3 for average acceleration. Right? 2-3 for average acceleration asks us to consider a situation in which a car is accelerating along a straight line road from rest to 75 kilometers per hour, and that occurs in 5 seconds. So for us to do this, we need to consider a car traveling in a straight line. Initially, the car is at rest. This term, at rest, right, it's what gets used in almost all problem solving for physics. And what it means is that the velocity is 0. It's not moving. There's no change in its position over time. So you can write that with any units that you want. It could be 0 meters per second, or 0 kilometers per hour, or 0 centimeters per nanosecond. Doesn't matter. At rest, 0, you can give it the units that you require. All right, so that's happening at time 1, the initial time. And as the car moves, its velocity changes. Its final velocity, its velocity at the second time, is going to be 75 kilometers per hour. So it was at rest and it sped up until it had a velocity of 75 kilometers per hour. This is a situation where there is acceleration because the velocity changed from 0 to this final number. We don't know how it made that change in this situation. All we know is that the change took 5 total seconds. So we can calculate the average acceleration here. The average acceleration is going to be the change in velocity over the change in time. We can set our initial time to 0 seconds, so that means that the total time it took was 5.0 seconds. And we know that the velocity, average velocity, is change in velocity is v2 minus v1. v2 is 75 kilometers per hour. v1 was 0 kilometers per hour. So that's going to give us a value of 75 divided by 5 seconds, or 15 kilometers per hour per second. Now, I want to let you know that there's nothing wrong with this unit reporting. Right? It's telling you how many kilometers per hour is changing every single second. But this is not the SI unit for acceleration, right? This is kilometers per hour per second. Acceleration, most of the time, what we want to do is we want to look at the rate of velocity change, where the rate of velocity change and the velocity are in the same unit. So what we're going to do is we're going to change 15 kilometers per hour, and we're going to change it into meters per second. Alright, and I'm going to do that by changing kilometer into meter and hour into seconds. Alright, and then that gives me .167 meters per second every second. I have two things that I have to do now. Two things that I have to do. The first one is significant figures. I should only have two significant figures, so I'm going to change that to 4.2 meters per second per second. And then the other thing that I'm going to do is I'm going to take a look at what this unit means. It means that every single second the velocity changed by 4.2 meters per second. Right. Another way of saying that, if I write this fraction style, it's 4.2 meters per second divided by a second. Alright, so that means that this value is actually 4.2 meters per second squared. And this is the SI unit for acceleration. And almost every situation, acceleration is going to be reported as meters per second squared. Alright, it's meters per second changing per second. Meters per second is meters per second squared. So what we want to look at is what this means. It means that every single second, so we'll come up with a situation where every second shows us a different value. Alright, so we could set t1 equals 0. Alright, at 1 second, right, our car's velocity is going to be 4.2 meters per second. Right, at 2 seconds, our car's velocity has changed another 4.2 meters per second. So that means that we could say that our car has a velocity now of 8.4 meters per second. Right? Because the acceleration of the car this whole time is 4.2 meters per second per second. So every single second the velocity is another 4.2 meters per second greater. Now one of the things that you want to take a note of is take a look at figure 2-10 in your textbook. Right? Figure 2-10 in your textbook makes a very specific point of showing you that because the velocity continuously increases, the displacement becomes further and further and further at each time interval. This is time equals 0, this is time equals 1, this is time equals 2, this is time equals 5 seconds. And they did a little cheat here and they showed, oh, the road extended out quite a bit here. The acceleration the whole time is constant, right? It's 15 kilometers per hour every single second. But the velocity is increasing at 15 kilometers per hour every second. Alright, so at time 1, velocity is 0. At time equals 1 second, velocity is 15 kilometers per hour. It's increased its velocity by 15 kilometers per hour. At time equals 2 seconds, alright, it has increased its velocity by another 15 kilometers per hour. So at 2 seconds, it's traveling at 30 kilometers per hour. The acceleration has not changed. At time equals 3 seconds, the velocity would be 45 kilometers per hour. And then all the way out to time equals 5 seconds, the velocity has increased to 75 kilometers per hour. There's a couple assumptions that we make here. We're assuming that the average acceleration is equal to the instantaneous acceleration. In other words, the car accelerated the same way the whole time. We make this assumption a lot when we're looking at 1D kinematics. so we're going to be taking a look at conceptual example 2-4. And I actually really like this conceptual example because it asks you to consider two different scenarios. All right, the first one, it says if the velocity of an object is 0, does it mean that the acceleration is 0? All right, so if velocity is 0, is acceleration always 0? And there's a couple of situations that I would like you to consider. The first one is, imagine that you have just jumped out of a plane. Right? The very second, the moment that you step out of the plane, you aren't falling. Right? At the very instant that you jump out of the plane, your velocity is 0. However, you know the second you step out of the plane, you are going to fall to the ground. So the very second that you step out of the plane, you know that you are accelerating because your velocity is going to start changing. Right, so jumping out of a plane is an example where your velocity at the very beginning is 0, but your acceleration sure isn't, because if your acceleration was 0, you would never fall down. You would stay there, stuck in the air forever. Another example. Imagine firing a bullet out of a gun. Right? In order for that gun to fire the bullet out, the bullet has to be given an acceleration. It has to accelerate from rest out of the gun. In order for that to happen, it has to have an acceleration. And that acceleration exists even the moment that the bullet starts its journey. And it starts its journey with a velocity of 0. Likewise, the bullet hitting a brick wall. The bullet has an acceleration the moment it hits the wall. The moment it hits the wall, it begins to decelerate. Right? It begins to decelerate, and if it gets stuck in the wall, right, eventually that velocity is going to be 0, but in that instant, it's still decelerating. We could use the same kind of concept for a watermelon hitting a wall. Right? Its velocity is going to be 0, but in that moment that its velocity is turning into 0, it has an acceleration because the watermelon started with a velocity when it hit the wall. It ended without a velocity, which means its velocity changed to 0, which means it had an acceleration at that moment. We can also consider if the acceleration is 0 doesn't mean that the velocity is 0. Let's think of some examples of that. The primary thing I want you to consider for your example for this is imagine a car traveling along the road. Right? Imagine that this car is using cruise control. Right? If you're using cruise control, then that means that your odometer is set at one speed and you're not changing it. Right? So imagine you're setting this at, let's say you want to set it at 60 miles per hour. All right, you're moving. Your velocity is a non-zero number. But if you're on cruise control, then that means that your velocity is 60 miles per hour here, 60 miles per hour here, 60 miles per hour here, 60 miles per hour here. Your velocity is a non-zero number. Your velocity here is 60 miles per hour. Your velocity here is 60 miles per hour. If we call this T1 and this T2 and this V1 and this V2, it doesn't matter. We could set this at 0 hours because it's always nice to start our time at a 0 point. And T2, it could be 2 hours. Right? If we're going to calculate acceleration, right, V2 minus V1 over 2 hours is going to be 60 minus 60 divided by 2. That's 0. No acceleration. That is a situation where your acceleration is 0 even though your velocity is not. These are the easier to consider situations because it's reasonable to say that you can have a non-zero velocity. Right? Your velocity just isn't changing. It's staying wherever it's set. Cruise control mode. Right? This is an easy situation to consider. Here you have to think a little bit more. Right? Anytime something starts from rest, its velocity is 0. Anytime anything comes to a rest, its velocity is 0. Right? If it stays at rest, then that means its acceleration isn't changing. But if it's leaving rest or coming to a rest, and that means its acceleration is not 0 because the velocity is changing. It's leaving rest or coming to a rest. So this brings us to exercise A, and I really like exercise A. In fact, I think I did exercise A earlier in this lecture. We're just going to keep things in scientific. We're going to take things out of scientific notation and put them back in. So imagine a car, all right, and you really want this car because this car has an awesome engine. In fact, this car can accelerate from 0 miles an hour to 60 miles an hour in 6 seconds. That's the target. That's what the car commercials always want you to consider. So what does this say about the car? Does it say that the car is fast, or does it say that it accelerates well? All right, for this situation, we have to consider 60 miles per hour fast. Oh, if you were running, sure you'd say yes, but this isn't supposed to be advertising how fast the car can go. In fact, most speed limits across the country are higher than 60 miles an hour. So this isn't necessarily getting a fast car advertised. It's just saying that this car accelerates well. It can change its speed from 0 miles an hour to 60 miles an hour, and it can do that in a very short amount of time. So it's saying that the change in velocity for elapsed time is good. Alright, it's got an awesome average acceleration. The rate that its velocity can change is high. That's a car that we want because we want this car that the engine works really well inside of it. So the next example that we're going to take a look at is we're going to look at a car slowing down. Alright, here's our car. We're going to slow it down. Alright, so a few things for us to consider. Alright, we're going to take a car that slows down. It's going to move to the right along a straight highway, and we're going to choose that to be the positive direction on our axis, moving to the right. Alright, and remember, we're in control of our axes, so we could set it up any way that we want as long as we're consistent. Alright, so this automobile is moving to the right along a straight highway, and we gave it a positive axis, and the car puts on its brakes to slow down. So when it starts out, its velocity is 15 meters per second. So over here it's traveling at 15 meters per second. Every second it's traveling 15 meters. Then it puts on its brakes, and its velocity at the second time is 5 meters per second. So we've decreased our velocity from 15 to 5 meters per second, and that change occurred over 5 seconds. So let's consider. We want to calculate the average acceleration. Average acceleration is change in velocity over time. So we're going to be looking at v2 minus v1 over the elapsed time. It's going to be 5.0 meters per second divided by 5.0 seconds minus 15 meters per second. So 5 minus 15 is negative 10 meters per second divided by 5.0 seconds. That's going to give us negative 2 meters per second, or negative 2.0 because significant figures are important, meters per second squared. That right there is the car's acceleration. Alright, and here's a very important thing for you to consider. Our negative 2.0 meters per second squared in this situation was a car slowing down. But negative acceleration does not necessarily mean that a car is slowing down. Negative acceleration just means the acceleration happened in the negative direction on our axis. Alright, that's a negative acceleration. Alright, a positive acceleration means that the acceleration happened in the positive direction on our axis. And it's very important that you make that distinction because we normally consider a negative acceleration in our day-to-day lives. Right? We consider it to be a deceleration. Deceleration is not the same thing as a negative acceleration. They're not the same thing, right? A deceleration is just when the car's acceleration and velocity are in different directions. So consider along this axis, right? If we have the car and its velocity, average velocity is in that direction, right? A deceleration, an acceleration where the car is slowing down, that just means that the acceleration happened in that direction. Now in this example, right, this is a deceleration because the velocity is in this direction and acceleration is in this direction, right? Here the velocity is positive, the acceleration is negative. But that's not the only situation in which we could have a deceleration. Consider, if you will, right, a situation where velocity is in this direction and acceleration is in this direction, right? So what happens here is here velocity is in the negative direction and acceleration is positive, right? This is still a deceleration, right? So a deceleration, one thing that we could say is we could say that deceleration occurs when velocity and acceleration have opposite signs. Right? That would be a deceleration. So let's take a look at exercise B, which is just another close look at exactly what we've done here. Alright, a car is moving along the x-axis. Alright, so here's our x-axis, and where'd my car go? There he is, there's our car. So our car is moving along the x-axis. Alright, what's the sign of the car's acceleration if it's moving in the positive direction? So we have our car, he's moving along the x-axis, he's moving in this direction, so that means his velocity is positive. Alright, so if the car is increasing its speed, right, moving in this direction, it means that its velocity started low and sped up. So that means that the acceleration is in the positive direction. So its acceleration is positive in this situation because it's increasing its speed. So increasing speed when the car is traveling in the positive direction would be a positive acceleration. If it's decreasing its speed, right, if its velocity is in the positive direction, but here it's starting with a high velocity and over here we have a low velocity, right, that means that acceleration is happening in this negative direction, right, and that's decreasing its speed. Alright, so that's what's happening when velocity is in the positive direction. Now we can consider, right, if the car is moving and its velocity is negative. Right, if the car is moving in the negative direction, right, now let's consider if it's moving in the negative direction and it's speeding up, then that means its acceleration is happening in the negative direction. Speeding up as it's backing up, right? This would be increasing speed. Right? The car is changing its velocity so that its velocity's magnitude is increasing, and that means that its acceleration is in the same direction as the velocity. Alright, that's a negative acceleration that caused the car to speed up because velocity and acceleration have the same sign. But if we slow the car down, if it's decreasing in speed in the negative direction, that would mean the acceleration was in the positive direction, and that's decreasing its speed. Right. So in this situation, it started with a high magnitude velocity and slowed down. Its acceleration was in the opposite direction of its velocity. Right. So it all comes down to sign. Sign is everything when we talk about acceleration and as a vector quantity. So that brings us to our last topic that we're going to talk about. We're going to talk about motion at constant acceleration. This is the beginning of 2-5. When we talk about motion at a constant acceleration, there's a couple of situations that I want you to think about. The first thing is that when we talk about constant acceleration, or when we talk about when acceleration is happening, for our physics class, we're going to consider that acceleration to be constant, which means that for the most part, we're only going to be considering average accelerations, or situations where the average acceleration is equal to the instantaneous acceleration. Right? When that occurs, we call it uniform accelerated motion. That means that the motion is happening with acceleration that is uniform from point A all the way to point B. From the initial all the way to the final, the acceleration is uniform, constant. Right? That means that the instantaneous and average acceleration are equal to each other the whole time. Uniform motion, on the other hand, is motion that has no acceleration. The velocity was constant, the same velocity all along the point of the way. All right? So for uniform motion, it's pretty straightforward. Right? In that situation, acceleration is 0. So that means that this is the only equation that you're going to need. Right? You're only ever going to need to calculate the average velocity, because there is no acceleration, there is no direction change, there is no going back and forth. So that means that the average velocity and the instantaneous velocity will always be equal to one another. So calculating the average velocity is enough. And since we can always set our initial time to 0, we can use this equation to solve for any problem where there is no acceleration. This is always going to work. All right? It's all you need. So consider, if acceleration is 0, if there is no acceleration, all right, we could say, Benny, here he is. Hi, I'm Benny. See how his name is outside of the speech bubble? Benny is telepathic. He said this part out loud, and then he said Benny inside of your head. So you're terrified of Benny. But Benny is traveling with uniform motion. He is traveling with a velocity of 5 meters per second. So we could figure out anything we want, because Benny's acceleration is 0. Alright, Benny doesn't accelerate. He just says scary things inside of your head. Alright, so if Benny's acceleration is 0, and his velocity is 5 meters per second, then we want to know if he walks toward you for 10 seconds, starting from a position that we could call the beginning position, x0, and we'll say that he started from 2 meters along an axis. If he travels with a constant velocity of 5 meters per second, what is his final position going to be? Well, we know he didn't accelerate, so this is all we're going to need. 5 meters per second equals x minus 2 meters divided by 10 seconds. Solving for x is going to give us 50 meters minus 2 would be 48 meters. Benny was able to travel 48 meters in 10 seconds. So just something to consider. 50 meters is pretty quick in 10 seconds. So here's you. Alright, you look worried because Benny is telepathic. Alright, Benny is not only telepathic, but he can levitate. Be my friend, Benny says. Alright, and he's levitating. He's off the ground, but he's traveling with a constant velocity in that direction of 5 meters per second. So if you're in a classroom with Benny, it will take him less than 6 minutes to make his way over to you. So make sure that you can run faster than Benny. Alright, so that's going to take care of any situation where acceleration is 0, but uniform accelerated motion is any time that acceleration is not 0. If acceleration is not 0, then that means velocity changes. Alright, and this is all as deep as we're going to go in this talk. Alright, if acceleration is not 0, then that means that you can use this as your approach. Alright, if acceleration is a 0, then we can solve for any piece, initial velocity, final velocity, or time using our acceleration equation. Alright, and in this case, acceleration is going to be the same whether it's average acceleration or instantaneous acceleration, because the motion is uniform. We consider that acceleration to be the same all the way across. So we're going to be able to solve for some of the variables here. So let's take a situation where Benny is evil. No, Benny, no! Alright, he's still levitating off of the ground. And here you are. You're a little worried because this is evil Benny. Alright, and evil Benny started from rest. Alright, which means that we give its initial velocity as 0 meters per second. And we will say that you are a total of 2 seconds away from Benny. Alright, it's going to take Benny 2 seconds to get to you. What will Benny's final velocity be if his acceleration is 14 meters per second every second, or 14 meters per second squared? Alright, so evil Benny's pretty quick. Right, 14 meters per second every second. That's almost as fast as that car that can accelerate from 0 to 60 meters per second. In fact, let me go back and take a peek at my numbers because I've already let them fall out of my head. A car that can accelerate from 0 to 60 miles per hour is 60 times 1609 divided by 3600. That's 27 meters per second every second. So Benny is just a little slower than that awesome car that you want when it comes to his rate of speed change. So we're going to determine his final velocity because we've got 14 meters per second squared, and that equals v minus 0 meters per second divided by 2 seconds. Alright, so we're going to multiply both sides by 2 seconds, and then we have 28 meters per second equals his velocity when he finally smacks into you. Just to give you a little bit of perspective, 28 meters per second is about 62 miles. No, that's not right. 28 meters divided by 1609 gives you 0.017 miles. Alright, and then we have to multiply that by 3600 to give us 62.6 miles an hour. Yeah, you and Benny are not going to have a good day together. So that kind of gives you an idea of how acceleration works, the difference between uniform motion without acceleration and uniform accelerated motion. And we will pick up with our next lecture from the textbook on how to solve for all of the variables in a situation involving uniform accelerated motion.